Hello everybody and welcome back to Calculus at Frederick Community College. In this video I will talk about continuity of functions at a point. So we'll go through the continuity checklist and look at some examples of various functions that might be continuous at certain points. And then in the next video I will talk about continuity over an interval. So you can think about it as part 1 of the lecture about continuity. Okay, so let's go ahead and take a look at the following continuity checklist. We say that in order for a function to be continuous at a point A, the 3 conditions need to be satisfied, and all 3 must be true. First of all, f of a has to be defined at that point, or in other words, a is in the domain of the function. Then the limit of the function exists as x goes to that fixed point A. And not only does it exist, it also has to be equal to the value of the function at that point. So if any of these conditions are not satisfied, then we say the function is discontinuous at that point. So the first 4 examples are from your textbook, and they kind of give you visual representation of what continuity at a point is. And it's pretty intuitive. You basically say, okay, if there is no jump or hole, no rip in the graph, then the function is continuous. So I'm going to do problems 5 and 6, and then 7 and 8, I'm going to leave it for you to practice. Okay? So let's take a look at problem 5. They ask us to find the points at which the function is discontinuous, and then also determine which of the condition is violated. Okay, so I'm going to write my solutions over here. Let's take a look at the graph for problem 5. Okay, let's see. The points that we're going to look at are 0, 1, 2, 3, 4, and 5. So I'm going to go ahead and list points 0, 1, and 5. Okay, let me highlight them. These points right here, 0, 1, and 5. This is where the function is undefined. So condition 1 is not true. Okay, we have a hole and no other point for x is equal to 0, 1, or 5. Okay, so the function is discontinuous at those 3 points. Condition 1 is not satisfied in that case. Okay, let's see. Let's take a look at x is equal to 2. X is equal to 2. That function is defined as x is equal to 2. Okay, and the limit exists, but the limit is not the same as the value of the function at 2. So that's condition 3 that's not satisfied. Okay, you can see that the limit is the same, right? As we approach from the right and from the left, the limit is 3, but the value of the function at 2 is not 3. Okay, one more point to consider. X is equal to 3. X is equal to 3. The function is defined at 3, yes, but the limit does not exist because the left and the right limits are different. Okay, so that's condition 2. Okay. Now you might be asking, is there a point at which the function is continuous? The answer is yes, there's a lots of them, but here's one right here. Okay, at 4, the function is defined. The function has a limit, okay, and it's the same as the value of that function, which is 2. Okay, and pictorially what? We don't have a hole, we don't have a jump. The graph is continuous. Okay, so that's 5. Let's do something similar for 6. Okay, which points I'm going to take a look at? I'm going to take a look at 0 through 5. Okay, so points 0, 3, and 5. 0, okay, 3, and 5. Once again, this is where the function is undefined. Condition 1 is violated. Okay, let's see. Point 1. The function is defined, the limit exists, but the limit is not the same as the value of the function, so that's condition 3. Okay, and what else do we have? X is equal to 2. Okay, x is equal to 2. The function is defined at 2. The limit does not exist. From the right, we get 2. No, I'm sorry, from the right we get 3, and from the left we get 2. Okay, so that is condition 2. All right, so use examples 7 and 8 to answer this question. Okay, what are the points between 0 and 5 where the function is discontinuous? It is pretty clear what they are, but then also try to identify which of the condition is not true. Okay, so now let's go ahead and do a lot of examples where we're dealing with algebraic expressions. So no more graph, right? So we want to see if the function is continuous at a given point without looking at a graph. Okay, what do we do in this case? Your number one step would be to determine if the function is actually, if a number that's given to you, so in the first example if a is equal to -5, is in the domain of the function. Okay, so what's the domain of this function? The domain is all values that don't make the denominator 0. Okay, so we want to get rid of everything that makes the denominator 0. So x squared plus 5x is not equal to 0, which is equivalent to say x can't be 0, x cannot be equal to -5. Okay, so the function is not defined at a, which means discontinuous. Discontinuous or not continuous at -5. Okay, what's the condition that doesn't hold here? Condition number 1. The function is undefined at -5 and 0, but we'll only ask for -5. Okay, all right, let's take a look at the next example. What's the domain of this function? Same as before, this is a rational function. So we need to take the denominator and see what makes that denominator 0. Okay, if I factor it, so when you factor x squared minus 9x plus 20, that's x minus 4, x minus 5. So the domain is all values except +4 and +5. Once again, it is not in the domain. We say the function is discontinuous at +4, right? And same as before, condition 1. Okay? So whenever you're dealing with a function that's a rational, or it might be a radical function, it could be trig function, your step number 1 is to determine the domain of this function. Then, if it's not in the domain, if the point that you're dealing with is not in the domain, automatically the function is discontinuous at that point. If it is, then we have to check other 2 conditions. So let's go ahead and take a look at the piecewise defined function that looks like this. Okay, we have a rational function x squared minus 16 over x minus 4 for all values of x except 4. Okay, so that's what this line says, and then 9 if x is equal to 4. So in this case, I'm going to go through the checklist and check all 3 conditions and see which ones are true and which ones are false. And if just one of them is false, that means the function is discontinuous. Okay, so condition number 1. All right, g of 4 is defined. So that condition is good. Okay, condition number 2, I need to see if the limit exists. So the limit as x goes to 4 of this function. Okay, now remember, if I plug my numbers in here, I'm going to get 0 over 0. This is the case of removable discontinuity, right? So if you recall what we're going to do, we're going to factor, right? So we're going to factor the top. We're going to get x minus 4 times x plus 4 over x minus 4, which will let us get rid of one of the factors, right? So x minus 4 is a common factor. That cancels out. We can evaluate the limit and we get 8. So the limit does exist. Condition number 3, the limit is 8. The value of the function is 9. Not the same thing. Okay, so g of 4. So this last condition is the one that is not satisfied, which means g is not continuous at x is equal to 4. Okay? And that's typically the strategy to use this checklist in this order. Check number 1. If it's true, keep checking. If it's false, you can stop right there. Okay, 1 is true, check number 2. If it's false, this is where we stop. If it's true, we have to check one more thing. We check number 3. If the limit is the same as the value of the function is continuous. Otherwise, it's discontinuous. Okay? All right, let's take a look at another example of a piecewise defined function. Okay, I have another example where I have a rational expression if x is not equal to 3. And then a fixed number 2 if x is equal to 3. Okay? Same steps as above. I'm going to go ahead and write g of 3 is defined. Check mark. Done. Let's do the limit. Limit as x goes to 3 of g of x. Again, this is a case of a removable discontinuity. Okay, so if I plug in 3 on top and bottom, I'm going to get 0 over 0. So the top factors nicely. What do we get? X minus 3 times x minus 1, right? Over x minus 3. We're going to cancel out this term right here. Now we can evaluate the limit. 3 minus 1 is equal to 2. Okay, that works. One last thing to check. Limit as x goes to 3 of g of x is indeed the same value as g of 3. Okay, right here, this 2. We want to make sure that these two values are the same, and they are. All 3 checklist conditions are satisfied. We say that the function is continuous. Yes, g is continuous at x is equal to 3. Okay. All right. So here you have 2 examples of piecewise defined functions where one is not continuous at that point and the other one is. Okay, so these are good practice examples. Okay, let's take a look at a couple of more examples and then we'll stop this lecture and we'll revisit continuity over some intervals. So let's take a look at the following example. I want to know if my radical function, square root of x minus 4, is continuous at 1. Just like before, all we need to know what the domain of the function is. So the domain of this function is what? Okay? Anything that's under the radical needs to be greater than or equal to 0. Okay, so really the domain is all values that are to the right of 4. Okay, so that x is greater than or equal to 4. 1 is not in the domain. Then we say f is not continuous or discontinuous at x is equal to 1. Okay, why? Condition 1, 1 is not in the domain. Okay? So 5 would be okay. 10 would be okay. Negative 17, not so much, okay? So anything that's to the left of 4 is not going to work. All right, let's see, problem 6. I have a polynomial function. Polynomial functions are nice, they're continuous everywhere. The domain is from negative infinity to infinity, or you can say all reals. It's the same thing. Okay? So the answer is yes, of course it's continuous. Yes. Okay. It's continuous for all values, regardless of what you pick. This is a parabola, right? So it opens up, and there's no gap for any value of x. There's no hole, there's no jump. All right, so that's your polynomial functions. Next example, we have a radical function. For radical functions, we don't say that it's automatically all real numbers, right? So for radical functions, we need to see what makes the denominator 0. So what is the domain? The domain is x is not equal to plus or minus 1. Or you can say we go from negative infinity to negative 1, not including, right? From negative 1 to 1, and from 1 to positive infinity. 5 is in the domain, so the answer is yes. Okay? It is continuous at any point except the ones that make the denominator equal to 0. Okay? I think that's everything that we're going to cover in this lecture. Okay, so there's one more video that will cover continuity of functions over integrals, and that will involve a lot of trig functions. Thank you for watching.